right, should we go ahead and get started? Give it a few more minutes, maybe.
I'm happy to get started if you guys want to get started.
Okay, awesome.
Yeah,
So,
no problem.
Hey everybody, I wanted to welcome you guys to the February Technical Activities Committee Workshop. Today's topic is lessons from building air leakage testing in Seattle. We'd like to thank our sponsors for allowing us to provide you with this free event, and they are Mechanical Sales Incorporated, Train, McDonald Miller, McKinstry, ATS Automation, Proctor Sales, PAE, Johnson Barrow, Dorsey and Company, Rushing, Aereps, Cezanne, Columbia Hydronics, and Viegas. So thank you to our sponsors. Our speaker today is Jose Estrada, and Jose is a senior building scientist specialist with JRS based in Seattle. With over a decade of consulting experience, Jose has provided technical consultations on all types of projects, ranging from low-rise residential buildings to multi-billion-dollar high-rise type A office projects. His experience also spans borders, having worked on projects in the US, Canada, Mexico, and across China. And with that, we are going to turn it over to you, Jose.
Great, thank you. Let me share my screen here. Okay. So while that's loading, I will try and keep the talk to about an hour, but I'm happy to answer any questions that might pop up along the way. So there we go. So I'm going to talk to you about the exciting world of whole building air tightness testing and how to embrace the test. So this is AIA accredited. So for one hour, it's self-reported, of course, and course description. And our learning objectives are here. So these are the standard AA front slides. With that said, I kind of want to step back a little bit and take a look at the larger context of the conversation that we're going to have. As Shay mentioned, I'm a building envelope engineer, a building science engineer, and I get asked a lot what exactly that is. It's a bit of a nebulous title. So people often ask me, what do these engineers do? At which point I kind of need to step back and say, what do any engineers really do, right? Because there's a lot of stuff that we do, but it's kind of hard to mention sometimes. And after thinking about it a little bit, I think we can break it down into its very component parts. Ultimately, what I do and what all engineers do is we have phenomenal goals. And what that means is we like to have goals that control different phenomena. So for us, it's enclose this space, separate this from that, and then other engineers, of course, tackle different phenomena, right? Make this sink, make that quieter, make that taller, make this spin real fast, make this really cheap, make it buildable. So for us, ultimately, what we do is we enclose space, and that includes everything around the building enclosure that does that. And we do this through the engineering process. And what that is basically we'll take our phenomenal goals and we'll distill them down into their quantifiable variables. And then once we know those variables, we can establish some metrics, and then we can analyze those metrics. Once we understand those metrics a little better, we can find ways to improve them and control the results. And then ideally, in a perfect world, we would rinse and repeat. We would do this over and over again until we find some optimized solution, depending on the project or whatever we're trying to do. So for the enclosure, here we have our building. And when we look at the building enclosure through the lens of a building scientist, what we have are four fundamental variables. We have heat. So that's just the energy within the air itself, the air molecules vibrating around. We have liquid water, which in this planet, of course, falls from the sky. We also have gaseous water just kind of floating around in the mixture we call air. And then we have the mixture of air itself. And the building enclosure often does more than just this. So it needs to protect the occupant maybe from hazards like fire, for example. It needs to be resilient and last the life of the building, and sometimes it even functions as structure. It needs to keep the space that you're in quiet so that we can sleep and enjoy our time inside of it. But we are going to focus mostly on the four colored variables here, and specifically what we're going to talk about today is this variable, air. And in doing so, we're going to go through some of the background of what this means to me and to to my peers in the industry. We'll look at how what that means fits into kind of the world of codes and code language. Then we're going to talk about the actual test itself and what that test means in a practical sense. After understanding the test a little better and how it fits into codes and how it fits into the background, we'll look at some of the results. And then we can see how those results inform the design. And after that, hopefully we'll come to some conclusions and some final just kind of takeaways from this conversation. So when we're looking at air, it's good to understand kind of what that is exactly. So the sea of gas we live in here on the planet's surface is mostly made up of nitrogen. And then there's a little bit of oxygen, which is the, we use to breathe and to support life. And way down here, there's everything else. So argon is a trace gas, and then there are other trace gases. And one of which is that one of our variables, water vapor, which can vary quite a bit depending on where you are. But there's also carbon dioxide, helium, and so on floating around in our mixture that we call air. This combination of gases basically forms the environment. It forms our weather. It is what stores, it is what holds and what we perceive as temperature, right? The little gas molecules vibrating around, pressure waves going through this, through this mixture make the sound that we hear. Water, of course, falls from the sky and it gets mixed into this bulk mixture. And also, this mixture contains pollutants. And when we're talking about the building air barrier or building air tightness and how it fits into the larger picture, I think pollutants is one of the items that's overlooked sometimes, because the air tightness of a building enclosure, it's very fundamental. It ties all of our variables together. And we as a group of engineers, right, as the next kind of up and coming generation of designers of the built world, have major tasks ahead of us. One of them is addressing global climate change, right? How do we fix this mess that we've put ourselves into? In the interim, we have conditions that look like this. So as Shay mentioned at the beginning, I've worked quite a bit in China, and specifically in Northeast China. And photos like this are famous, right? So there is a problem with air pollution in many developing cities in the world that we live in. And while there's a larger challenge for us, for humanity in general, to tackle the cause of this pollution, the cause of this global climate change, I think there's a valid space for airtight design in buildings to allow us to make safe spaces where the air is safe to breathe in the interim while we're kind of working through that as a society. This is another image of Beijing, where it's common to wear a face mask, right? But it's not just limited to China. That seems to be the most famous example. This is an approach into India. I believe this is New Delhi, where we can see similar challenges with pollution. And it's really not even limited to the developing world. So this is Paris, where smoggy days are famously becoming much more common. I first gave this presentation in California, and of course, Southern California is also famous for its air quality issues. And I like to think that we here in Seattle, up in the Pacific Northwest, are immune to this, but this was the view coming north on I-5 just this past summer, where Seattle is starting to experience smoke season. And for a brief period of time, our air was some of the worst air out there. So, despite our mild climate, I think air barriers have a practical application just kind of globally. When I say air barrier, it's important to not confuse that with ventilation. So any healthy building does need a certain amount of air exchange to replace just kind of the stagnant air in the building. Ventilation is basically the building breathing, right? And like any body, it breathes through a controlled space. So we breathe through our nostrils, goes into our lungs. Ventilation, the way we see it, it's healthy, it's required, it's needed. But as far as the building envelope wants to treat it, we want to treat it in a controlled manner where we know what's coming in, we can treat it, we can condition it, we can clean it. Air leakage, on the other hand, is that uncontrolled stuff. The stuff that's exiting and entering the building just kind of in locations where we didn't really plan it to do that. So it's uncontrolled, it's unknown. Really, it's wasteful, right? Because that air, we put a lot of energy in the unit to condition it to some comfortable temperature. So we have our occupants, they're in our building. And the way we apply those variables, air, water, thermal, to our building enclosure is through what we call, in the building science world, control layers. And when we're looking at control layers, there's a great many number of ways that we can apply them to each other. But I'm going to look at a very basic way that we can do it just in the interest of time. So there is an idea of a universality for some types of building enclosures. So we call this a universal kind of wall approach. And what that means is we have our so in this example where we're looking at the slab on grade, it's surprisingly elegant, right? Because we can put our thermal control, if there is one, down underneath everything, and then we have our air, water, and vapor all combined into one very thin layer onto which we cast our structure. This is an assembly that can work in almost any climate, cold, hot, moist, dry. If we were to take that and flip it on its head, we would have a very universal roof assembly, right? So basically it's the structure, and the structure sits inboard on the conditioned side. There's some air, water, and vapor control above it, and then our thermal sits on top of that. Of course, there's a lot of practical reasons why we don't see this assembly everywhere, but we know conceptually that this is an assembly that could work almost anywhere. Take that assembly, turn it on its side, and we have what's considered a universal wall. And at fenestrations, we can see that there are what I like to refer to as a subway map of changing in plane and direction of where these control layers go. How these control layers tie into each other at interfaces is where I tend to live. So where I, as a building science engineer, tend to live and spend my time hopefully adding value to projects, right? This is where the rubber hits the road in terms of failure or success for any building enclosure. So let's dig into the background a little bit. It's important to have a common metric that we're following. So when we're talking about air leakage, consider that we have some volume of air. It's got some height, some width, and some length. We'll call it some unit volume. And we can normalize this unit in one of two ways, or we commonly do. So we can either normalize it by volume. So we can see how the amount of air inside this container changes relative to the volume, or we can measure the surface area of this unit space, this unit container, and see how the volume of air changes normalized to that area of that container, the surface area. So some pressure is applied to this container, an amount of air is exchanged, and then these are basically the two units. So if we normalize it to the surface area, then that's where the unit cubic foot per minute per square foot of surface area of the container at some reference pressure. Or we can see how many air changes would have occurred in an hour at some other reference pressure, and that's the volume normalized approach. The challenge with these two, so both of these units have their pros and their cons. The challenge is they don't easily interchange between them. So for example, let's look at this example. If we were to take a target of 0.4 CFM, which is the area normalized approach, and that's a very, that is a code approach, or it was in one of the previous codes, we can see that under code, this container would have 2.4 cubic foot per minute allowable air leakage to meet the code under an area normalized approach. But if we were to take that exact same CFM and look at it in a volume normalized approach, it's very high. That's about 144 ACH. Of course, our buildings aren't 1 foot by 1 foot by 1 foot. So the relationship between the two it dramatically drops as the building gets larger. But they still don't tie together very easily unless we have some more information. So most of our buildings fall within these lines. So the green line is the max, the blue line is the min for the data set that we're going to look at today, and the yellow is the average size of building that we're talking about. In the data set we're looking at today, if we were to just plot some of the results on a graph, where at the bottom we have the air leakage normalized by surface area, and in the y-axis we have the air leakage normalized by volume, we can see that there isn't really a direct relationship. We can see, I mean, in general, you know, as buildings get leakier, they tend to both get leakier together. But we can see some of the examples. I don't know if you can see my cursor here. So we can see some outliers, and those tend to be buildings that are either very large or very small, or some buildings that are leaky or tight but not very voluminous, rather. So those are our metrics. So we can see for area normalized, and since I'm talking to an ASHRAE crowd, you can let me know if you see anything funky here. But you know, 0.1 is generally considered ASHRAE tight, whereas 0.6 in an area normalized approach is considered generally ASHRAE leaky. And some of the more residential approaches then use the other metric. So they use the volume metric. So the 2015 residential energy code here is an ACH of 5, I believe, whereas passive house is closer to 0.6. So where do these numbers come from? It's important to kind of understand that too, right? Because at the end of the day, they're a little arbitrary, these targets that we set. In the engineering mindset, we generally allow it to kind of work like this. So we have a material. It's got some air leakage rate for that material that's some order of magnitude very small, so 0.004, let's say. That's like what we would expect to see if we measure the air leakage of drywall. So the engineering judgment says, well, if we have that material and we put it together into an assembly, you know, we'll allow an order of magnitude change in the air leakage, and that would bring us to an assembly air leakage of about 0.04 in this case. So the next logical step is when we take that assembly and put it into a whole building, we allow an order of magnitude change in that air leakage as well. So generally speaking, these are the orders of magnitude we tend to see and accept as an engineering community for air leakage. So now let's jump into the codes a little bit. So in the beginning, in pre-2009, there really wasn't a quantitative target in the Washington State or the Seattle Energy Code. Then in 2009, the code started mandating not only an air barrier, but a test to demonstrate air leakage performance. So for commercial buildings over a certain size, it was 0.4 was the target as normalized by surface area. Residential, it was about 7 ACH. In 2012, we switched over to the IACC, and the commercial target stayed relatively the same as the residential target went down a little bit. A lot of the buildings we're seeing today are being tested from the 2015 code, and I think really the future of kind of where we're going is going to be decided by people like the people listening to this presentation right now. So in 2016, while there wasn't a requirement for an air barrier, it's unfair to say that there wasn't an intent or a desire to have some ceiling of air leakage. This is the operative wording from the 2006 code, for example. So even though it doesn't say air barrier specifically, it does require building envelope sealing to minimize air leakage. And it was very prescriptive in how to do that. Seal around fenestrations, seal around junctions, and so on. In 2009 was when the actual word air barrier showed up in the code. The state of Washington required this for buildings over a certain height, in this case 5 stories. The city of Seattle took it further and required it for all buildings. Since this period, we started testing a lot of buildings as a firm, and we've just kind of been collecting data. So the challenge with this was that there was some anxiety on the market side. So financial partners working on a lot of these buildings or ownership groups were a little unsure of well, first of all, if a building could be tested to meet this, and what would happen if you didn't meet it. So the code in Seattle did clarify it, but there was still some confusion kind of on the market side. And to kind of to express why that brought anxiety to the market, we can kind of look at the CA timeline. So usually in design, we have our SD phase, or then we have our design development phase, and we go as a group to design the building in the CD phase, the contract document phase. And then we enter construction. And we know at the end, our goal is to have a certificate of occupancy. So let's say, if there's a below grade foundation, there's some digging, then for the building enclosure, there's some below grade work, maybe the building gets framed up, and then there's some roofing, and then there's a bunch of other stuff happening, interior work and so on. And at the very end, as we're approaching the date for our certificate of occupancy, we go through a process similar to what I have up here. So there's always little things left over. And generally speaking, what we ran into very early on was this mild panic as the team realized that the air barrier wasn't completely done, and we had to pass this test that no one knew if the building could pass or what would happen if we didn't. So then the air leakage test occurs way at the very end. Sometimes the building is ready to move in, and the air barrier test is happening the day before. In 2012, the wording was clarified a little bit. So we can see here that the building shall be tested to meet this target. And if the test rate exceeds the target, then here is the path to compliance. So that helped alleviate some of the anxieties on the market side. And similarly, this is the 2015 code, the previous one was the 2012. Similar wording except with a different target. And then of course in 2018, the IACC has similar wording, and the challenge is here in Washington State, testing is required. In other jurisdictions, testing is not necessarily required, as there's other ways to comply with the air leakage approach. And one of them could be to use the right materials or the right assemblies and so on. So let's look at the test. The test is quite simple. So we'll just walk through it step by step and kind of see how it works. So this is an example building that will be tested. We have an unknown, that's our air leakage. So what do we know? We know that this building has some geometry, so it has some building enclosure surface area. We have a fan, and we can calibrate our fan. So the fan will extract or push in air at some rate that we can measure. We can assume at these pressures that air is incompressible. So the amount of air exiting or entering this container is being replenished through other spots in the container, and that's what we're looking for. So the way the fans are built, we can measure the speed through the fan. We know the opening of the fan, so we can get a volumetric airflow. And if we combine that with a manometer, so put a manometer in some part of this container, we can measure the pressure difference across the enclosure. And that's basically all you need. So if we were to turn the fan on and let the building or let the container pressure stabilize to some pressure, whatever it could be, so in this case it's 46.7, we see that there's an associated flow rate that will stay the same. Then if we turn the fan up a little bit, we'll get some other flow rate. And we can do this multiple times, and then we'll get a curve. So we can see that the function for this is an exponential. So Q, being the volumetric flow rate, is proportional to some constant times whatever the difference in pressure is raised to some exponent. And what we're looking for is that constant and that exponent. We can see that the volumetric flow rate here is on the y-axis. The reference pressure that we're measuring is on the x-axis. And if our points are regular enough, and the ASTM that we follow provides a guideline for how accurate the points need to be, then we can build a certain level of confidence in our curve, and then we can get the results in whatever unit we want. So we can either normalize it by volume, by going to whatever the reference pressure is. So volume is typically normalized at 50 pascals. And we see here that, at that volume, we have a CFM of 19,000, almost 20,000 for the building, and that relates to an ACH of 0.5. Or we can reference it by enclosure area. That's typically normalized at 75. So the reference pressure is typically 75 pascals. And in that case, we can see that this enclosure had a leakage of 0.159 CFM per square foot. So this building, or this example, is quite a tight building. The test allows you to either test the building by pressurizing it and measuring that air leakage, or depressurizing it and measuring that leakage. And it's generally good practice to do both. We find that depressurizing the building usually results in a tighter test. And that makes sense because a lot of the gravity dampers and the components of the building enclosure that are designed to kind of open to exhaust air, or doors perhaps open outwards, they will close shut when we depressurize the building, and we won't measure the air leakage through some of the intentional openings. Whereas pressurizing the building does open those a little more. So the code, generally speaking, allows us to take both of these and then average them to get a result. So looking at the limitations of this test, one of the big assumptions is that the container that we drew is an open container. So there's no interior walls, no interior partitions, no interior floor lines, just a big open box, which we know isn't the case. So when we're doing this test, we need to make it as much of an open container as we can. If that blue highlight that follows the perimeter of the building enclosure is our line of air tightness, or our boundary of air tightness, we need to make sure that air can get to it in every room in the building. So all these doors need to be propped open. If we were to put a manometer here and another manometer here, we would want those two pressures, when we're measuring our volumetric flow rate, to be more or less the same. Otherwise, we're not really getting a true reading, because the pressure in one portion of the building will be compelling air to go in at a different rate than the pressure at another end of the building. We also assume calm conditions. So if we're looking at wind, for example, which is what these arrows are indicating, and we were to put our reference pressure out here, you would notice that it would be a different reference pressure than if we were to reference it from here, which would also compel air to come into the enclosure at different rates. And likewise, we also assume relatively small pressure differences, and that ties into stack effect. So some of the challenges with this is if the building gets too tall, we might have to put up with, or we might as a testing team need to deal with the stack effect in the building. So if we have a tall building like this example here, and someone turns on heaters, there's a certain amount of air leakage that occurs. Heat will start to rise through the building, and then we have a situation where there's air will want to rush into the building at the lower floors, and it'll want to rush out of the building at the upper floors. So if we were to test it and that stack effect was too great, similar to our previous example, the readings would not be true or not be true enough. Some more practical challenges with testing too are access to power. These fans tend to be quite high power, so they'll each need to be on their own circuit. The approach that masking is done, and I'll jump into masking in a little bit, also can have an impact on the test results. And also people. So because this is occurring at a very busy time in the construction schedule where lots of people are trying to rush to finish the job, it's often necessary to test at odd hours. So after hours, overnight, on weekends, just to get the time to have the building to ourselves so that we can close every window and every exterior door, open all the interior doors, and do all the prep that's necessary to get the building ready to test just the air control boundary. Let's look at stack effect a little bit more closely. So the ASTM, which in this case is ASTM E779, has an equation to tell you whether or not the conditions are good or ideal to test. And that's basically the temperature difference across the enclosure times the height of the building needs to be less than either 200 meters Celsius or 1180 foot Fahrenheit. So there's also the masking approach. So we can mask generally in two ways. The building enclosure, as I said earlier, when we're talking about air leakage, we're talking about air coming into the places where we don't want it to come in. But there are places where we do want air to come in and go out, where we want venting, where we want air intake, and so on. And the approach that we take as an industry right now is we want to remove those from the test. We don't want to test those. Otherwise, if we did, we would need to really make that leakage, the allowable leakage, a lot greater because we would have a lot more leakage. So you can either mask those. Practically, you can mask them either from the outside, like what's shown here. We can mask it from the outside at the roof. This is a vent that just gets masked on the outside, and just mask them right from the outside, or we can mask them from the inside. So vents over ranges, vents from heaters, and so on, or from laundry machines, and so on. And while we're testing, we can also test qualitatively. So we can use smoke pencils, infrared cameras to test where air leakage is occurring. Here's also an example of the setup that we tend to use. This is the fan, and just needs to go into an opening and so on. And like I said, IR is another technology that we can use. So generally speaking, if there's a pressure difference across the enclosure, we can see air leaking if it causes the location it's leaking out of to change in temperature. It's typically seen as streaking, which this example, I mean, there was a big hole here, so the streaking isn't quite as evident. But when using infrared thermography, the thermographer just needs to be careful that what they're seeing is air leakage and not thermal bridging or reflections from the sky or so on. So you'll definitely want to make sure someone who's experienced is doing that. Let's hop back into the stack effect though. So there are a lot of tall buildings coming online in Seattle, and several of them have already been tested. So if we look at this building, this is another project here in Seattle. It will be tested. It's not done yet. And if we were to follow the ASTM approach for checking the stack effect, we would look at the height of the building. We would go down to the grade, which is what that equation requires, not from the bottom of the building, but from grade. And we would have some height. And if you were to turn on a heater, then what would happen is air would rise, hot air would be buoyant and rise, and then we would have cold air rush in to replace it at the bottom, and that hot air would blow out of the building at the top. the place in the middle is called the neutral zone. And that's kind of a nice place to be where there is no air rushing in or out of your window when you open it. But depending on how the leakiness is of the enclosure, we can actually change that neutral zone. So we can move it up or we can move it down. Or in some climates where it's very warm, Florida or other warm places, this can actually happen in reverse. So if we turn on our ACs in the building and cold air, which is heavy, starts to slowly work its way down the building, we can actually reverse the direction of this stack effect. So in this example, we have a building that's 350 feet. And I gave this talk in California. So what I did was I decided, okay, well, if we wanted to test this building as just one big zone, what would our options be in terms of when we could test? We can't change the height of the building. We can't change the temperature outside. So when can we test this? So this is the average temperature. This is the average day temperature in Seattle in the summertime. The stack effect would be too great for that. So for the average day temperature in the wintertime in Seattle, it's way off the charts too much. So we wouldn't be able to really test that day either. In California, on the average summer day, we wouldn't be able to test that day either because the stack effect would be too great. So in this example, if this building were in California, we would only be able to test on the average winter day. And this is in Southern California. So what do we do? The allowable temperature difference across the enclosure is 3.3 degrees Fahrenheit. So when I said we can't change the height, I kind of lied. So we can kind of change the height of the test. So we could, for example, let's say we put a fan here onto the 26th floor and we apply a pressure to this building, we would start measuring the leakage out of that enclosure. The challenge is we would also measure the leakage through the floor. So in order to offset that, we would need to put another fan in the floor below and pressurize it to the same pressure so that we're not compelling air across that floor. This is called a guarded test, and it would allow us to test a sample of the building by making it a little bit shorter. And we can do that, for example, here we could do it at the top of the building, or if we wanted to take that approach and test some random floor in the middle, maybe to get a check, we would similarly apply a pressure. We would want to test just those two walls of the exterior, so we would need to add a fan above and below so that we're not measuring the air leakage across the floor. This has some practical limitations. For example, there are shafts that run through these floors continuously, like those stairs or at elevators. So we would need to make sure that we're considering those when applying this test. Okay, let's look at some results. So this is the market that we're talking about. So Seattle has a lot of very cool high-rise buildings, kind of densely packed into a downtown core. But for the most part, Seattle is a fairly mid-rise city. I would argue that most of the construction that we've seen, at least in the residential sector, has been what we call mid-rise mixed-use, 5/2, 7-story kind of style buildings. And that is the majority of what we have seen tested. Buildings that look like this. So for simplicity, let's just focus on these buildings then. So what I did was I went through our data, and isolated those buildings. So if we were to look at buildings by height, this is what the data looks like. And to explain the chart a little bit more, on the x-axis, we have the building height in stories. On the y-axis, we have the measured air leakage as normalized by surface area. And we can see that 1-story, 2-story, 3 buildings are really short, small buildings. They're kind of all over the map. I wouldn't say necessarily that 2-story buildings are on average leakier than other buildings. What I would say, though, is that when a building is small, the results we find tend to be a lot more variable. Whereas as the building becomes taller, we find that the results tend to normalize a bit more and, in fact, become tighter, become less leaky. That doesn't mean big buildings are just in their nature less leaky. Usually big buildings also have different materials that just allow them to be less leaky. But also, if there was a discontinuity in some location of a large building, the impact is felt less intensely. when we look at it by surface area, so for example, here we have these 3 bars. The bar on the left is buildings with a building enclosure surface area of under 50,000 square feet, and then so on. So the one in the middle is up to 100,000 square feet, and the one on the right is greater than that. We can see that the results tend to normalize a lot more. Smaller buildings still have that little bump that show them a little leakier, but that's more so because smaller buildings just are more variable, is what we found. Another way to look at the building size versus the air leakage is to consider what we call the volume ratio. So recall that we can measure the amount of air leakage in 2 ways, right? By volume and by surface area. If we were to take those two and take the ratio of them, where the volume is over the surface area, we would get what's called the compactness ratio. So on the x-axis here, we have buildings that have a low compaction ratio. And then as we move over to the right, we have buildings with larger, progressively larger compactness ratios. And then our y-axis, of course, is our air leakage. And we can see, similarly, smaller buildings, or buildings that have a smaller compactness ratio, they show here as more leaky, but what we find really is that they're more variable. And as the building gets bigger, it's just much more regular. So there are 2 common technologies that we see for the air barrier that's applied to the wall of the building. And that's either a mechanically fastened water and air barrier or a fully adhered water and air barrier. So the mechanically fastened would be something like a Tyvek commercial wrap or a Vapor Shield IT or something along those lines. Whereas a fully adhered would be something like a Vapor Shield SA or a Grace's adhered product or something along those lines. What we find is that in this set that we look at, if this is the target, so here at the bottom we have the air leakage rate, and on the y-axis we have the percentage of buildings that meet that rate. And then we have the 2015 target at 0.3. We see that both of these technologies for wall air barrier can be made to meet that target, the targets we're looking for. So what this tells us is that it's not necessarily the wall air barrier type that will make or break whether or not we meet our target. There's always a few that have trouble meeting it, but it's not necessarily that technology itself that's going to be a driver. We find that it's more the actual other design decisions that make that choice. So for example, here's another look. So there are 2 ways we can close the lid of our container. We can either do it by what's called a vented roof assembly or an unvented roof assembly. So in an unvented roof assembly, those are the traditional conventional roof systems where below the roof system you're inside, whereas a vented roof assembly is similar to what we would see in a single-family home, with a vented attic, where the ceiling of the top floor is the air barrier. And what we find is that there is actually a difference in performance between these 2. So if we were to put our code target here for 2009 at 0.4 and our 2015 SEC target or our 2012 SEC target at 0.3, we see that buildings with vented attics tend to have a harder time meeting these targets. So what this says to me is that it's not necessarily that a building with a vented attic will not meet the target, more so that the decision between a vented and an unvented roof has a larger impact in the early design phases than the decision of which type of WRB to use. If we look at the testing by code cycle, we can see that here again are our targets. We can see that generally speaking, buildings that we tested were more or less meeting the target. But what we notice is that if we look at the buildings by when they were tested, this market tends to be kind of getting used to the test. So we can see here, if we show by code distribution or show the testing by code cycle. Blue is the 2009 code. We can see that in this cumulative distribution chart, we'll put in our targets here, 80% of the buildings tested met the 2012 and the 2009 code. Whereas in 2012, we can see the difference in the building. So for example, 2009, buildings tested in 2009 actually did a better job here meeting that code, but let me actually explain that a little bit more. So when we look at buildings, regardless of when they were designed, when we look at buildings that we tested in 2012 and in 2013, this is what the chart more or less looked like. So at the bottom, we have the air leakage rate, and on the y-axis, we have our relative distribution rate. So 50% of the buildings tested fell at around the 0.2 mark, and so on. That's how you read this chart. The following year, 2014, 2015, this is what that chart looked like. So for whatever reason, it became a much flatter curve. So we had buildings testing very tight, but also some very leaky ones. When we tested buildings in 2016, we noticed that our results started to get much more narrow around the 0.3 mark. And then in 2017, we start to see those results start to shift towards the left, being more tight. And then in 2018, we saw those results on average shifting even further. So what this says to us is that even though there's always challenges, I think there's a bit of a learning curve for the market when whole building air leakage testing is introduced. But generally speaking, this market at least was able to adapt, kind of learn from the first few tests, and really start pushing buildings to be quite tight. Let's look at design a little bit. If we were to look at this example that we did our thought experiment and tested here together, how do we make it airtight? How do we design it to be airtight? So really, just like with any design, we have to start big and then work our way in. So we know that any building will have our container geometry. It'll have a top, it'll have some sides, it'll have a bottom. So that's your first step, defining what these are. Here in Seattle, we need to identify on plan and in elevation what that boundary is. And when considering each assembly, we have to identify what the different pieces are doing. So for example, here we can see that the air barrier vapor retarder occurred down at the structural deck. Then we have our thermal control layer above it and our water control layer above that. Similarly, in this case, in a wall, for example, we can either do our air control at the back on the interior, or we can do our air control at the exterior, that water and air control membrane, but then we would need to, of course, control for vapor inboard. So as long as the team knows where these different layers are and which one specifically is the air barrier, we can always connect the dots at their interfaces. Similarly, at bottom of slab, we can see here air barrier running underneath the insulation. So identifying where all those are is really the first step. This is an example of an air control boundary. And it's important to also note that the air control boundary for the building, which in this case is this very dark hatch, doesn't necessarily follow the exterior of the building. And that's a location that's often missed. So for example, this trash room that we're looking at here, let me see if I can zoom in. This trash room here has an exterior wall, so some passerby on the street would look at this building and see just a continuous exterior wall, but we would need to design this wall so that this trash room is outside of the air control boundary. So the next step is putting these pieces together. So walls meet roofs, and they can, walls also do a lot of funky things in this market to make the building look good. And that's fine. It makes our job a little bit more challenging because the building enclosure likes to be very simple. So even if the building cladding is doing really cool stuff, the control layers like to be as flat and straight as possible. So in this case, for example, we have our air control boundary. We can see that trash room again. Let me see if it highlights here. We want the air control boundary to very simply kind of follow this path. At the bottom of wall, it also needs to follow that path here. At the top, even though the wall does shoot up past the building, we want our air control boundary to be a very simple turn. And that brings us back to that conversation, that early design phase decision of vented versus unvented roof. So on the left here, we can see an unvented roof. So our air control boundary, which in this case, the vapor barrier, air barrier, is a membrane on the roof deck that goes under the parapet and turns and adheres to the wall air and water barrier. That's a very simple approach, and it's very continuous, right? So here we can see our water and our air control kind of splitting at the bottom of the parapet where the air control follows it's continuous underneath the roof assembly. Whereas in a vented assembly, we see that our air control boundary leaves the wall and then follows our drywall. And above it, there's insulation and then also a vented attic. So this graph, the purple portion being the vented and the blue portion being the unvented, this is basically how they look in a practical sense. This is an example of an unvented roof assembly and what that looks like in real life. So here we can see the membrane underneath that parapet. And here's what it looks like from the roof level. Whereas in a vented assembly, we can see that it's much more complicated. So conceptually, it's very easy to use an airtight drywall. Drywall is an airtight product, but the interfacing is so much more. There are more pieces. And usually when there's more pieces, there's more that you can do. There's more mistakes that can be made. So in this case, we'll draw in our drywall here. The drywall often has holes. So we can see here that there's wall, water, and air barrier on the outside. That air barrier needs to transition through the wall. So in this case, there's spray foam, but there are holes going through the stud or the head track here that need to be sealed. Then the drywall needs to seal to the wood. We can see that there are demising walls where the wall at the top is not continuous. That needs to be sealed. So it's just a much more complicated approach to maintain air barrier continuity. And then, of course, fenestration. So anywhere the air barrier interfaces with something else, it's important to understand where the air control is on the one component. So in this case, where the air control lives, the air control boundary lives on the window, and how it ties into the air control boundary for the wall. So here we can see that this window ties its air control boundary at the interior surface. And that's similar for the head and for the sill. For a curtain wall, also similar. So curtain walls tend to carry their air and water control boundaries at their shoulder. So we can draw that in like this. And for a unitized curtain wall, these are also a little interesting because unitized curtain wall, they carry all of their control layers at the shoulder, but designers like to fly curtain walls past floor slabs. It makes it a little bit complicated to maintain the air barrier continuity. So if we zoom in here, we can see that even though the curtain wall flies past, we want to tie back that air control back to the slab. So what that looks like in a detail sense is something like this. So here we have our air control from the roof assembly. We can see the air control meandering through the curtain wall here, through the glass, into the curtain wall shoulder, and then into a sheet metal backcan. But we need to seal the two, and up here, basically at the shoulder, or as close to the shoulder as we can possibly get. And if we were to take this and flip it upside down, it's a similar approach. So if we were to draw in our control, even though it looks like and feels like we can seal to the back of a curtain wall, we really need to understand where the air control is in the curtain wall system and seal to that, which in this case is at the shoulder. And then at penetrations through the wall air barrier, this stems back to the conversation about ventilation versus air leakage. So here we have our air barrier on the wall, and we have some intentional opening. In this case, it's a vent. We can either seal when we're testing here at the vent location and isolate this vent directly where it meets the air barrier. And if we were to do that, we would be testing basically this line. But if we were to seal that same vent penetration at the side on the inside where it meets some appliance, so for example, if we were to seal the range hood instead of the vent itself at the wall, we would be testing the air barrier on the wall plus whatever the ductwork is that extends back to wherever we're temporarily sealing. This can have a material impact on the results sometimes. We've been doing a little bit of testing to figure out what that is, or a little bit of experimentation as part of when we're testing buildings, just to get a better idea. And I'll make sure to update the group here when we have those results. So, and then there's specifications. So for specifications, having the right materials is important, but having the right mindset is almost more important. So the first thing to do is in design is to set an expectation and set an understanding among all the players, including the construction team, as to what the target is. So the target in this case is for an airtight building of some performance level. This gives the construction team a chance to, for example, limit parties handling the air barrier, share high-level goals with their subs, and also assign ownership of this task to their subs. Then during construction, the next step would be to sit down with all the parties who are going to touch the air barrier and basically go over the intent more thoroughly. Then during construction, there can be air barrier QA/QC by the construction team. And then a final check just before the test. So this allows the team to be a lot more prepared for the test, and then also be able to catch discontinuities in the air barrier before they're covered up. So that's more or less what I have for you today. Some takeaways that I'm hoping that you'll take from today are that the test itself is a little bit, if you're not familiar with the specifics of the test, it can seem a little daunting. It's actually quite a simple test. As long as you understand its limitations and its goals, this is something that I think has allowed the industry to make better and tighter buildings, and it's really not that complicated to do, although there is a learning curve. It's important to communicate the test goals to everyone before construction starts. I also want to highlight that building airtightness is a very fundamental portion of the building enclosure. And we have the technology to build buildings quite tight today. So really what it takes is the next step is how we use the technology we have to how we put those components together is really what is needed. So design matters, but execution matters more. And then also interfaces are more important than clear walls, because interfaces tend to be where the majority of the leakage happens. And lastly, the fewer trades that we can get to touch the air barrier, generally speaking, the better. The fewer parts there are, the fewer people there are touching it, tends to result in a tighter building because it's easier to maintain ownership over that design. And lastly, one thing to walk away with too is we're often asked when we sit down in an early design meeting with clients, hey, I want to target some building air tightness X, 0.25 or something more stringent than code, for example. And usually what I would say is, well, that's fine. Generally speaking, we can't really design an air barrier to a specific number. So for example, we don't have one design that's a 0.4, CFM target, and then a different design for a 0.25. It's really the same. You either have air barrier design or you don't. What changes and what gets us to the more tight air barrier, or to the more airtight building is the execution of that design. And that's my talk. So I'm Jose with JRS, and feel free to shoot me any emails. I'm a millennial, so you can follow me on social media too. Are there any questions or anything? Great. Well, I appreciate your time.
Awesome. Thank you very much for that awesome topic, Jose. We really appreciate it. And this lecture was recorded, so it will be posted online on the ASHRAE webpage. And like he said, if you guys have any follow-up questions, feel free to reach out to him. Thank you.
Thanks, guys.
Thank you very much.